For this video, what we're looking at is evaluating a limit using the properties of limits. We're going to call this direct substitution because all of these properties are going to allow us to do a direct substitution. Our first property. So the limit of f of x as x approaches c does not depend on the value of f at x equals c. Because a lot of times we can't get that value. It may happen, however, that the limit is precisely f of c. It's just plugging that value in. In those cases, we can evaluate the limit just by doing a direct substitution. There's no reason to put in values close to that value because we can just plug that value in. The reason we couldn't do that earlier when we were doing it numerically was because those values were undefined. They didn't exist at x equals c. However, for some that do, we can just do a basic plug in, right? Plug and chug. Now here are your limits and where these are going to apply to. Your basic limits. The limit of a constant is just that constant. Example. And I'll write it right here. The limit as x approaches anything, 52 of 7 equals 7. Because there's nothing to plug in, right? It's always going to be 7. It's a constant. The limit as x approaches c of x, well, we're just doing x approaching c. We're just going to plug in c. We get c. The limit as x approaches c of x to the nth power. Once again, there's no restrictions here. There are no undefined points. There are no, what's the term we use when we're looking for restricted values, right? There are no restricted values. So c to the nth power. We're just plugging in c anywhere there's an x. What if we're multiplying something? Notice that here we're making an assumption that the limit of f is L, the limit of g is k as x is approaching c. So if we take the limit of a constant times a function, then that's just the constant times the limit of the function. Okay? Now what we've already done, the limit of 2x squared as x approaches 2. This means that this is 2 times the limit of x squared as x approaches 2. We can plug the 2 in. 2 times 4, we just get 8. But notice, there's no reason to go through this whole process. Just plug the 2 in, right? 2 squared is 4. 4 times 2 is 8. That's all you got to do. Same deal with this. If I have the limit of a sum or difference, that's just the sum or difference of the individual limits. So now we can look at polynomials. If you've got the limit as x approaches 1 of x squared plus 3x minus 4. Well, this is just an exponent. So I know from the previous one that exponents we just can plug in. So I can plug that in. Here we've got a constant times x, and I know that x we can just plug in. Here we've got a constant, which I also know is just a constant. So I just plug in 1 squared is 1, plus 3 times 1 is 3 times plus 1 is 4, minus 4, I get 0. So plug and plug. The product, the limit of a product is the product of the limits. Once again, just plug it in. Same with the quotient. As long as k is not equal to 0, as long as this limit doesn't equal 0, because that would give us an undefined, then we're just going to take and plug in. Same deal with a function to a power. We just take the limit to that power. But this is all the exact same thing. This is just plugging that c in wherever we have an x. Now the limit of a polynomial function, 4x squared plus 3, is just that value when we plug x equals 2 in. 2 squared is 4, 4 times 4 is 16, plus 3 is 19. This is direct substitution, and it is valid for every polynomial, okay? And any rational function that doesn't have a 0 denominator. So from here on out, if we take the limit of something and it's just a polynomial, or it's just a rational function, or if it's just a radical, or if it's just a quotient, these things, as long as I don't have a non-zero denominator or a restricted value, then bam, I've got it. Okay, just plug it in. This is the actual theorem, which tells us that if I'm taking the limit of a polynomial, I can just plug the c in. Now, this is also going to apply to radicals because they're still algebraic functions that have no holes in them. Now, there are undefined places, particularly when you've got an even root with a negative number, right? You can't take the square root of a negative number, the fourth root of a negative number. But this is still an exponential, right? This is c to the 1 over n power. And we know that we can do this because of our previous theorems. Now remember, this is only going to be valid when n is odd or when c is positive and n is even, because you can't take the square root of a negative number. Another one, composite functions. This is when we're talking about things like, well, honestly, the square root function. If you're taking more than just the square root of x, if you're taking the square root of 3x squared minus 4x, that's a composite function because we're putting a polynomial inside of a radical. Now, when we do this, basically you're going to take the limit of the inner function and plug that limit into the outer function, right? Absolutely, but there's no reason to do it. All you have to do is just plug it in. As long as you can plug a value in and you do not get something that is undefined, then do it, okay? Don't think about it, just do it. Last thing we're going to look at is trig functions. Notice that all of our trig functions there are no weirdness in them, okay? As long as c is in the domain, then we plug it in. Like I said, if you plug in, for example, here, if we did the limit as x approaches pi over 2 of tangent x, can I plug pi over 2 in there? No. Why? Because it's undefined. So that doesn't work, but as long as you can, what about if it was x equals 0? Here we can because tangent of 0 is just 0. So as long as it's defined, you can go ahead and plug it in. So what does this mean? As long as there are no discontinuities, which are holes in our asymptotes at the particular value of x, all we have to do is plug the value into the function. This is called direct substitution. Now, when does direct substitution not work? Well, it doesn't work if there are discontinuities, which means if there is a fraction with a 0 in the denominator, right? Because that's undefined. Or if you've got a trig function that's undefined. Okay? Now let's do a couple of examples real quick. And these are going to go really fast. There's no reason for them not to. All right? What's the limit as x approaches 2 of 3? This is a constant. The limit of a constant is just the constant. The limit of x as x approaches negative 4. We just plug negative 4 into x, we get negative 4. The limit of x squared as x approaches 2, we're just going to plug 2 in. 2 squared is 4. What about finding the limit of 4x squared plus 3 as x approaches 2? This is a polynomial. We know with polynomials, we just plug it in. 4 times 2 squared plus 3, that's 4 times 4, which is 16 plus 3, which is 19. What about this one? Once again, we've got a polynomial. Now, there are restricted values here, right? I know negative 1 is a restricted value, but I'm not going to that restricted value, so I could care less. I'm going to plug it in. 1 squared plus 1 plus 2 over 1 plus 1. That's 1 plus 1 is 2 plus 2 is 4 over 2, which is 2. What about here? The limit of the cube root of 2x as x approaches 4. Once again, we've got an odd, so it doesn't matter whether the thing is even or not, but it is. So we can just plug it in. What's the cube root? What's the cube root of 4 times 2, which is 8? Cube root of 8 is 2. All right. Composite functions. Once again, as long as I can plug it in and have no problem, I've got no problem. Now, 0 squared is 0. 0 plus 4 is 4. Square root of 4 is 2. 3 squared is 9. 9 times 2 is 18. 18 minus 10 is 8. Cube root of 8, also 2. Now, here's something interesting. I'm going to look at my composite function a little bit differently here. I'm going to tell you right away that the limit of f of x as x approaches c is 64. If I have this, then I know that this is equal to the cube root of the limit as x approaches c of f of x, right? I can take that cube root all the way on the outside because it's a composite function. So I know that the limit of f of x as x approaches c is going to be 64. So we're talking about the cube root of 64. So what's the cube root of 64? Cube root of 64 is 4. Okay? What about this one? The limit as x approaches c of f of x over 16. Once again, this is a composite function. So I'm going to actually say this is actually like saying the limit as x approaches c of 1/16 times the limit as x approaches c of f of x. You see how I can separate those two? Because it's a product, right? This is like saying 1/16 times f of x. And I know that the limit of a product is the product of the individual limits. So since this is a constant, it's just a constant. The limit of f of x is 64. So I've got 64 divided by 16. So what's 64 divided by 16? That's 4. What about here? The limit as x approaches 0 of tangent x. I did this just a second ago. I can just plug that in. Tangent of 0 is just 0. What about here? I can just plug that in. Pi times cosine pi. So what's the cosine of pi? It's -1, negative pi. Here we can plug that 0 in. We just get sine squared of 0. Well, sine of 0 is what? That's just 0. What's 0 squared? That's 0. So we've seen a lot of different ones, but they all come back to the same principle. Just plug it in. If it works, you've got your answer. If it doesn't work, maybe we've got other techniques that we can use, and we'll talk about them in the next video. So if you have any questions, shoot me a remind or ask a question in class.